everyone! In this lecture, we will learn about logical operation instructions. First, let's have a general understanding of logical operation instructions. The logical operation instructions we will learn include AND, OR, NOT, and XOR, which are common logical operations. As the name suggests, logical operation instructions are commands that perform logical operations. Among them, AND, OR, and XOR logical operation instructions are all dual operand instructions. The requirements for operands in these instructions are exactly the same as those for the MOV instruction. The NOT logical operation is a single operand instruction. Its requirement for the operand is that it cannot be an immediate value. When using logical operation instructions, pay attention to their impact on flag bits. The impact of logical operation instructions on flags is somewhat different from that of arithmetic operation instructions. For example, except for the NOT instruction, the execution of other instructions will affect all flags except the AF flag bit, and regardless of the execution result, they will clear the flag bits OF and CF. This is something you must pay special attention to. The last point is that the execution of the NOT instruction does not affect the flag bits. Now let's learn about the logical AND instruction. The logical AND instruction is a dual operand instruction with the opcode, and its function is to compute the bitwise AND of two operands and store the result in the destination operand. It can perform an AND operation between two 8-bit operands or two 16-bit operands with no carry or borrow in the result. However, the word length of the two operands must be equal. The AND instruction has three main application scenarios. Scenario 1. Compute the bitwise AND result of two operands, such as AND BL/SI. This instruction calculates the AND result of BL and an 8-bit data in the memory unit pointed to by SI. The second application scenario is to retain certain bits of an operand while clearing other bits to 0. The principle here is that a number ANDed with 1 remains itself, while ANDed with 0 results in 0. Thus, in this scenario, design an immediate number with zeros in the bits to be cleared and ones in the bits to be retained. For example, the instruction AND AL0FH clears the upper 4 bits of AL, while preserving the lower 4 bits. The third application scenario is to clear the CF and OF flags, while keeping the operand unchanged. This scenario leverages the fact that AND operation always clears CF and OF regardless of the result. For example, the instruction AND AX computes the result of AX and itself, meaning 0 and 0 or 1 and 1, leaving the value unchanged. But after the operation, CF and OF will be 0. Let's look at a specific example to see how the AND instruction is applied. The problem requires reading a byte from port address 3F8H. If bit 1 of this number is 1, then a word starting at the address. Data can be output from port 38H. This problem involves the application of input or output instructions and the AND instruction. Here, the input data is obtained using an input instruction. After obtaining the data, the AND instruction is used to check whether the data meets the condition. If the condition is not met, the data is fetched again from the port. If the condition is met, an output instruction is used to output the data as required by the problem. Based on this logic, we can draw a flowchart and fill in the instructions to complete the program. Next, let's draw the flowchart for this program. Read data from the specified port. After obtaining the data, we check whether its bit 1 is 1. Second, if it is 1, data is output from another specified port. If it is not 1, the data is read again. This is the entire process. Now that the flowchart is complete, Let's review it. The first step is to read data using the IN instruction. Since the given port is 3F8H, which exceeds FFH, the port must first be moved to DX, and then the data is read from DX. The final step is to output data using the OUT instruction. Similarly, since the given port also exceeds FFH, the port number must first be moved to DX, and then the data is output from DX. The intermediate condition check step is to determine whether bit 1 of the data is 1. We need to know that the least significant bit is bit 0. So bit 1 is actually the second least significant bit. Therefore, the immediate value to be ANDed with this data can be designed as 0 to H. When the result of the AND operation is 0, it means bit 1 of the data is 0. When the result is 0 to H, it means bit 1 of the data is 1. Alright, let's now look at how the specific program is written. Typically, a program will have an initialization part to set the initial values stored in memory units, etc. However, this program does not require setting initial values, so the initialization part can be omitted. Next, fill in the data reading part. First, use the MOV instruction to transfer 3F8H to DX. Then, use the instruction to read data from DX into AL. Since the problem requires reading a byte, it is sufficient to read it into AL. Next, fill in the judgment part and AL with 0 to H. If the result is 0, read the data again. If the result is not 0, continue execution. Here JZ is a jump instruction that checks whether the operation result is 0. If it is 0, it jumps to the WAIT position and starts execution. If the operation result is not 0, it continues to execute the next instruction. Next, fill in the output part. Use the MOV instruction to transfer 38FH to DX. Then use the MOV instruction to transfer the memory of 2 consecutive units starting from DATA to AX. And finally, use the OUT instruction to output the content of AX to the port specified by DX. The above is the usage of the AND instruction, which is the foundation for learning other logical instructions. In the next lecture, we will learn the usage of other logic instructions. See you next time.